The topic now is internal resistance of the battery or cell. So basically, what is internal resistance of a battery or a cell? The battery or cell itself, it's having some resistance. So there is some loss voltage is there inside a battery, and that loss voltage is due to the resistance of the battery. We call that as internal resistance. Example, you have a cell. On the cell, it is labeled EMF of the cell is 1.5. So on the cell, it is labeled that its EMF is 1.5. You connect a bulb here or a lamp. So what should be the voltage across the lamp if you connect this bulb parallel to the battery? How much voltage will be there or potential difference across this bulb? If you connect parallel to the cell or the battery, in this example, it should be 1.5. But practically, it is not 1. It should be 1.5, but theoretically 1.5, but practically it will not be 1.5. A bit less than 1.5, even unused cell. So what is the reason? What happened from where there is a voltage loss if the cell on the cell it is labeled 1.5? So it means some of the energy or some of the work is done per unit charge to move in another component. So what is that component? That is actually the internal resistance of the battery. So battery itself, it's having a resistance, and we call that as internal resistance. So how we represent that? To represent a battery with the internal resistance, we'll make a cell, symbol for cell, and next to that we make a resistor, and this is inside a rectangular box which shows basically a cell with internal resistance. If we are only drawing this symbol, it means the cell is without internal resistance. We neglect the internal resistance, but practically there is internal resistance, so some loss voltage is there. So when we connect a bulb or a lamp, so why the lamp was not receiving the same voltage? The reason for that, like example, if the electromotive force or EMF of the cell was 1.5, some of the voltage like 0.05 lost in the internal resistance, so remaining is actually transferred to the external circuit, which is 1.45, and the loss voltage is in the due to the internal resistance of the cell. So the concept of internal resistance, cell or batteries also have a resistance which leads to loss in voltage, and when it leads to loss in voltage, we call that as internal. The main source of this loss voltage is a internal resistance. So if I connect a voltmeter, when I connect a voltmeter parallel to the battery, so voltmeter cannot record the loss voltage because voltmeter is connected here. So what the reading on the voltmeter will be there? It will be 1.45 volts, because 0.05 of energy or work done per unit charge is against the internal resistance. So remaining is actually what the voltmeter will record. So voltmeter will not record the maximum voltage here as there is a current. So if there is a current, there is some energy loss within the internal resistance or work done per unit charge when charges are moving through the within the cell. So the voltmeter will not record the same voltage as labeled on the cell. So how we represent that? A cell with the internal resistance, the equation which relate, so maximum voltage which or the EMF which the cell can provide is E. The internal resistance is denoted by small r. To distinguish that it's an internal resistance, that's why it is denoted by small r. And the external resistance is denoted by capital R. Now what happened when we represent a cell with internal resistance? So it should be inside a box. This is showing a cell with internal resistance. So conventional current, the current I will move out from the circuit. The internal resistance and external resistance have the same current. Why the internal resistance and external resistance have the same current? Because the total external resistance is always in series with the battery, or in series, the internal and external resistance are always in series with each other. So the current I is moving through the circuit. The same current will pass through external and same current will pass through internal. So what is the voltage here? We have the formula V is equals to IR. So voltage here is I and capital R. And voltage at this point is I and small r. So basically the total voltage, the total EMF divided between the external and internal resistance. So we can say that the EMF is equals to voltage drop externally and internally plus internally. So EMF is denoted by epsilon. Voltage drop externally, that is IR. Voltage drop in I in capital R, and voltage drop internally, that is due to internal resistance I in small r. And external voltage drop can also be denoted by V. So we can say EMF is equals to V plus I R. So this is a formula which relate internal voltage, external voltage and EMF, or this formula relate internal resistance and current in the circuit with the output voltage and the total voltage. EMF is the maximum voltage which the battery can supply. But if the current I is zero, if the current is zero in the circuit, if no current is moving through the circuit, there is not a complete path. So if I is zero, this whole factor will be zero. In that case, the EMF is equals to maximum voltage of the, or EMF of the supply. So the voltage is equals to EMF of the supply. So basically, if the circuit, in the circuit, if it's an open circuit, no current is moving or flowing, then there is no voltage drop internally. So when we connect a voltmeter, that time the voltmeter will record the maximum voltage, and we call that maximum voltage as electromotive force. Is it clear, this part? Any doubt in this? Any question or a doubt? So graphically, how we can find the internal resistance, finding internal resistance and EMF? So if you want to find the internal resistance and or EMF of the cell, so we will sketch a graph between the current on x-axis and voltage on y-axis. We have the formula that the EMF, we have the formula that EMF is equals to V plus IR. V is the external voltage and IR is the internal voltage. But I want to sketch a graph between V and I, so I have to rearrange this equation like y is equals to mx plus c. So on y-axis I have voltage, so I need a voltage, other should be separated. So EMF minus IR is equals to V, or I can say V is equals to EMF minus IR. That's the same thing, I just switch the places. but on x-axis the quantity which we plot on the x-axis should be next to equal to. So we are plotting current on x-axis, so I will rearrange the right hand side. So it will be minus I minus IR or minus RI is the same thing, plus EMF. Now I will compare with the equation of straight line, which is y is equals to mx plus C. So on y-axis, if I have voltage, on x-axis, if I have current, what will be the gradient? The gradient will be, gradient of this graph will be minus R. And what will be the y-intercept? The y-intercept is equals to EMF. Now, what will be the shape of the graph? How this graph will appear? First, as you know, we have this equation, EMF is equals to V plus IR. If there is no current in the circuit, if current is not flowing through the circuit, it's not a closed circuit, that case EMF and voltage will have the highest value. Like voltage will have the highest value, we call that as EMF. But then what happened, we connect a circuit. When we connect the circuit, the current start to flow. As the current start to flow, the current increases, so voltage drop internal, because the sum of external plus internal voltage is equals to EMF. So when the current is moving through internal resistance, so voltage drop internally will increase, so voltage drop externally will decrease. If we allow greater amount of current to pass, if we increase the current, the external voltage will decrease. So when we plot these results, it will show a straight line. So this will represent a straight line, and increase in current will reduce the potential, the voltage across the terminals, because more inner voltage drop internally and less voltage drop externally. So you have this formula. Now you can see the y-intercept, the point where it intersects the y-axis, that's called a y-intercept. So y-intercept is equals to EMF, and the gradient is equals to minus R. So using a graphical method, we can also determine the resistance of, we can internal resistance of a cell, or we can also find the EMF. Is it clear? The graph and why the shape of the graph is like this? Because V is the external voltage, and external voltage decreases as you are increasing the current. Because when you are increasing the current, more voltage internally or more energy loss or voltage drop internally, and less voltage drop externally. Is it clear, this part? Then example of internal resistance. Example, if you want to provide a ignition to or the self to the car engine. Example, this is a headlight, and there's a battery inside. Example, you switch on the headlight. So when you switch on the headlight without giving an ignition or self to the engine, the lamp will light up because there's a voltage, the current is moving. But then what happened when you provide an ignition to the car? When you provide ignition, it will draw more current, great, because some of the current is going through the lamp and the sum of the current is going to this self or ignition circuit. So means you are drawing greater amount of current or taking out greater amount of current. When you take out greater amount of current from the battery, because the voltage which EMF, we have the formula EMF is equals to output voltage plus internal voltage. Internal voltage is internal resistance multiplied by total current, the current in the circuit. So if the current in the circuit increase, if you draw too much current, what will happen? The voltage, internal voltage will increase. EMF is constant, so if internal voltage is increasing, external voltage will decrease. So if you draw too much current out from the battery, the headlights will become dim. That is why, like example, if you can do this, check this, observe, like apply this rule here. What you will do, you will just switch on the headlights and give ignition to yourself to the car engine. What you will find the moment you're providing a cell, the headlights will become dim. Why the headlights will become dim? Because when you're providing ignition, the battery is drawing, or you're taking out more current from the battery. So as you are taking out more current from the battery, more voltage drop internally and less voltage drop externally. That's why the brightness of the bulb or the lamp will, or headlights will decrease. Is it clear? Now, what is the maximum power? Now, at which condition the cell will provide maximum power? So you have three conditions. What are the three conditions? The first condition, when external resistance more than internal resistance. When external resistance is equal to internal resistance. And when internal resistance more than external resistance. So we'll compare the three conditions. All the cases will take the same cell. We have a 10-volt supply because the EMF of the supply, EMF is 10. Okay. We have internal resistance. Say this was 100, and the external resistance is, because if the external resistance is more than internal resistance, for example, this is 200. And a battery with the internal resistance, so we should surround this. The second condition, when internal and external resistances are same, like internal resistance is 100, external is also 100. That's the second condition. We'll do calculation to show in which one greater power is delivered. All the cases we have a 10-volt supply, EMF of the battery cell is 10 volts. And the third one, there is internal resistance and then external resistance. So this one is internal resistance is more than external. So internal, I'm not changing internal, external only I'm changing. So it will be 50. Now, when we want to find the power, because to get the power we need a voltage and we need current. P is equals to VI, or you can also use P is equals to I square R, because you know the external resistance, so you can use this formula. So to get the power, to find the power, we can use P is equals to V square over R, P is equals to VI, or P is equals to I square R. We'll use this formula I square R because it's easy to find the current we can find, and the resistance external is already given. So what will be the current here? The total current. So the EMF, because the total EMF is 10, the total circuit resistance is 200 plus 300, that is equals to 200 plus 100, that's equal to 300. So you have the formula V is equals to IR. So V is 10, I is a current which we don't know, and R is a resistance, the combined resistance, total resistance, because they are in series. So 200 plus 100, that's 300. So current will be 10 divided by 300. What's the answer for 10 divided by 300? 1 by 30. So that is 0.33. And we need a power, so P is equals to I square R. So I square means 0.33 square multiplied by resistance, the external resistance, because we are finding at which condition it will transfer the maximum power. 0.033, yes. So 0.033 square multiplied by 200. What's the answer? 0.033 multiplied 0.033 square multiplied by 200. So 0.22. The power which is transferred here is 0.22 watts. Then we'll do for the second one the same thing. First we'll find the total current. How to get the total current? This is 10. Uh, the total circuit resistance 100 plus 100, that's 200. So 10 divided by 200. So 0 will cancel with 0. 1 divided by 20, which is 0.05. Then we'll find the power, which is P is equals to I square R. So 0.05 square multiplied by the external resistance, which is 100. That is equals to 0.25 watts. And when we do it for the third one, V is equals to IR, total EMF is 10 volts. So 10 current we don't know, and the total circuit resistance is 150. So 150 is divided, other side it will 150 is multiplied, other side it will divide. So 1 divided by 15, that is equals to 0.06 ampere. And then again we'll find the power. So P is equals to I square R. So I is a current, 0.06 square multiplied by resistance, which is external, 50. So 0.06, that is equals to 0.18 watts. So what it shows, as you can see, 0.06 multiplied square multiplied by external resistance. External resistance is 50, so multiplied by 50. So what it shows, what condition it transferred the maximum power. You can clearly see from this calculation, the maximum power is transferred when the internal resistance and external resistance have the same value. When they are both same, the external resistance and internal resistance are having the same value, then maximum power is transferred. If the external resistance is higher, the power will transfer but small amount. If external resistance is less than the internal resistance, then the power will transfer but again a small amount. It is maximum when internal and external have the same value. Because What happened here? The total circuit resistance, the current is less, the external resistance is high, so the product of current and resistance is giving a power. And what happens? The maximum power is delivered when internal and external resistance having a same value. So when we sketch a graph for power output of a battery or a cell and external resistance or load resistance, means external resistance or load resistance and power. So what we will observe, what shape we will observe, the power will increase and then decreases. Maximum power is delivered. This maximum power or higher power is delivered. What does it mean? It means at this point internal and external resistance have the same value. Is it clear, the concept of power transfer by the cell or the battery? And it is maximum when internal and external resistance have the same values. Any doubt in this? Any question or a doubt? Now we'll do some questions related to electricity.